designed these rating systems. So they say that doctors actually don't recommend SPF 100 because that makes people think that for some reason that level of protection would be better or last longer than SPF 50. Now, SPF 100 lasts the same amount of time as SPF 30. So they all last the same amount of time. So what's most important is when we're applying sunscreen to our skin is that we reapply it constantly. As we sweat or if you go swimming, right, you've actually rinsed that SPF or sun protection factor off of your skin. So when you come out of the water, you need to dry off and reapply. And if you're outside, right, and you're sweating, you're also losing some of that as well. So just because the number gets higher doesn't mean it protects you for any longer. It just protects you from a higher percentage of those UV rays. Now, what's also really interesting is we're going to talk about UV light and what kind of things glow under a blacklight. So if you've ever seen a blacklight before, I actually have one right here inside this lamp. It glows kind of this funny purple color. We'll take a closer look at this without my green screen behind me. Now you might think, well, we talked about visible light in a different episode of Echo Live. We said that we're only able to see those colors within the visible light spectrum. We're not able to see UV light, and that is true. Since UV light falls closest to those purple colors, that is the color that we observe using a UV or black light. Now, what's special about this, though, is it really is emitting UV waves. We can't see them with our eyes, but we can see the evidence of those UV waves being emitted by looking at different things that fluoresce underneath a black light. So if you're not familiar with the phrase fluorescence, we need to take a look at another picture. So here is an example of how fluorescence works. We talked about fluorescent light bulbs, and this is actually the same process by which a fluorescent light bulb will glow. We talked about that if we excite the electrons inside these fluorescent materials, we can actually cause those electrons to go up in an energy state. So it jumps to a higher orbital, which is what's happening in this diagram right here. Simply telling us that eventually this electron will have to drop back down. So we gave it some energy in the form of a photon or in the form of light. That photon was absorbed, that energy caused it to jump up by an orbital, but eventually that electron will need to jump back down. When it jumps back down, there is some energy left over, which is actually emitted, which we see through this red arrow. So it's emitted as visible light. So when we see things that glow under a black light, all we're seeing is that emission of photons. We're actually seeing it release back out visible light. So while it's absorbing UV light, when it re-releases that energy, we see it on the visible light spectrum. So let's take a look at some objects that glow underneath a UV or black light. I've got some examples on a tray here. So I've got a couple rocks and a banana. So things naturally fluoresce, or some things are naturally fluorescent. So if I take a look at these, I'll actually switch my camera over so we can get a close look underneath our camera here. Turn off my virtual background, even though that looks pretty cool. There we go. So now we're just taking a look at the table. Always good to have a control, right? Now, if we take a look at one of our minerals or our rocks, we can see that some of it actually glows under a black light or fluoresces. So to our naked eye, see if we turn on our light here, to our naked eye, this rock appears gray. So it's a nice gray and kind of white color, not too special looking. But when we turn on the black light, we start to see some of those orange hues. We can see that even better if I turn off my studio lights. Take a look at that. Now, some minerals like this one, or even this slightly larger one, they naturally have those components that glow or fluoresce under a black light. So the minerals that compose these rocks have those abilities to re-emit their photons as visible light. Not all rocks can do that, obviously, only specific ones. So I've got 3 examples here. Here's one more. So even though these rocks, like we said, under normal light, so without the black light, they look something like this. Once we turn on the black light, we can see those fluorescent minerals starting to re-emit those electrons or photons as visible light. Now, I've got some examples of some other pictures just because I thought these were pretty beautiful. So here on the screen, we have two more minerals that glow under UV light. So it's not always orange that we observe. Some of the wavelengths of UV or light that's re-emitted from these minerals that glow under UV light are things like calcite. And under calcite under UV light can release green and orange, even some pink or reddish colored visible light waves. And then this one is called willemite. So we have calcite and willemite. So what could be a very fun activity is if you have a blacklight, or you have even better, a blacklight flashlight, similar to the one that I have right here. And you can very easily get these on Amazon. So if I turn off my studio light here, you could walk around and take a look around the beach, or take a look around another nature park and look for minerals or natural compounds that glow under UV light, which is pretty cool. Now, minerals aren't the only things that naturally fluoresce. We also have things like this banana. Now you can see that only parts of this banana are really glowing under a black light, and it's most noticeable where our banana is starting to get very, very ripe. So around these brown spots where the banana is starting to ripen, we actually start to absorb that UV light and re-emit it in a way that's invisible to our eyes. So again, to compare it, right, if we turn off the black light and have our light here, we definitely can't see those same circles surrounding these brown spots. They look pretty normal to me. But if we switch our light back over, we start to see some of that fluorescence from this banana. But tell me in the chat, can you think of a reason why things like bananas might fluoresce? Why would things like fruits and vegetables or plants, what could be a reason in nature that they fluoresce? Take a moment and tell me in the chat if you have a guess. Someone guessed maybe it's because of the potassium inside the banana. Potassium is definitely one of those vitamins which are important to people. Good guess. So we definitely know a little bit of background information about potassium. Let's see, we've got some guesses coming in on our different channels here. Zoe tells me she thinks it happens because they grow from the ground, and Maureen tells me maybe because of something is inside the peel. Well, what scientists theorize could be one of the reasons that plants, especially things like fruits, glow under blacklight is so that the animals that eat them or help to populate them will actually be able to find them. So if you remember back to our visible light episode, we said that visible light is different depending on the species. Now, while humans can see a full spectrum of color, which we define as color from red all the way to purple, bees see completely differently. So they don't see red as well as humans do, but bees and other insects are actually able to see UV light. We talked about how this can actually help them to be directed to the pollen on some of these flowers. Scientists actually theorize that bananas will start to glow under UV light as they ripen so that fruit bats are actually able to find them. So remember that even though in animals, right, we don't necessarily want to be eaten by other animals. We want to be staying safe. Plants rely on those things that visit their plants or eat their fruits in order to help spread their seeds or to help pollinate them. So scientists theorize that one of the reasons bananas will naturally fluoresce is to alert pollinators or things that eat them to be able to find them, because different animals can actually see those wavelengths of UV light that humans cannot. All right, so we've taken a look at a banana and some rocks. Those are some items that naturally fluoresce. Let's switch our light over here just to regular light for a moment. Not super bright, but I do also just have a white bag, just a white cloth bag. This is actually where I store this UV light between programs to our naked eye, it appears white, right? But when we wash things with white fabric in powder in laundry detergent, we actually add synthetic phosphors to that laundry detergent, which cause these things to glow under UV light. This actually makes whites appear whiter. So if you have white t-shirts, they're able to absorb these synthetic phosphors, which are fluorescent materials that we engineer in order to make our clothes appear whiter or cleaner, which is good, right? So we add synthetic phosphors to things like toothpaste as well. So even though your teeth are actually naturally fluorescent because of the minerals inside them, we can add things like these phosphors, which we have in laundry detergent, in order to make them appear to glow even brighter. Fun fact, another thing that is naturally fluorescent is actually your fingernails. So parts of your fingernails, not quite as bright, but parts of your fingernails will actually glow under UV light as well. Those are naturally fluorescent, just like your teeth, but materials like cotton is not naturally fluorescent. Instead, we add those phosphors, which we have in laundry detergent. Now, let's turn our studio lights back on here. And let's switch our camera over so I can show you another experiment that you're able to try at home. All right, now, using this clear laundry detergent, which we said we added those synthetic phosphors to, something that allows a material to become fluorescent, so adheres to those properties of fluorescent, which we saw in that picture, we can actually make things glow. So I have some clear laundry detergent here. This is OxyClean brand, and it works really, really well for it. It even says right on this label that it makes whites whiter. And so that actually is full of those phosphors, those things that make items fluoresce under blacklight. Now, what I'm going to teach you how to do using this is actually how to write secret messages that can only be revealed under UV light. So I'll switch my camera back over just quickly so we can take a look at this note that I've written before the program. So on my note here, I've given us some instructions that tell us how to write secret messages in UV light. But this isn't so secretive, right? Anyone who picked up this piece of paper could easily read it and would know what it says. The trick is, before this program, I actually took some of that clear laundry detergent and I wrote a message on it, which can only be revealed using UV light. So if I turn on my black light here, our secret message is revealed. So if you can read my secret message, go ahead and type it in the chat. Tell me what it says there. Just make sure that you're able to see it from home. So without the black light, right? Oh no. And with the black light, there it is. So I can show you how to do this using just some very, very simple materials. So if I take the cap from my laundry detergent here, place it near our secret message, scoot this over, we can see that this stuff glows under UV light really, really brightly. So those phosphors are again having a shift or a jump in their electron states. When they fall back down to their original state, they emit that as visible light, which we can actually see. Awesome. So glad everyone can see our light there. Now I'll show you what it looks like at first. So if we just go ahead and we add a note down here to the bottom, we can just draw something like a smiley face just using our Q-tip. If you'd like to write even thinner, you could always use a toothpick instead of a Q-tip. But you'll notice that if I turn my light back on right now, you can see it. So if I turn my light off, right now you can see it because it made the paper pretty damp, but it only takes just a few minutes for that to dry, and it'll end up looking just like regular paper like we see right here. So really, really easy to do. This is Echo Live insider information only. So now we're all in a secret club that can share secret messages that can only be revealed under blacklight. So remember that you can get the light bulbs like in my lamp from things like party stores. You can order them online like Amazon. And then I also have these nifty UV light flashlights, which work just as well for helping us to reveal our secret message here. Now, it's no secret that science rules, so I give you permission to share that with your friends. But this process will keep between us here on Echo Live. Sound good? All right, so let's switch our camera back over. And we've got one more experiment to try using something that fluoresces underneath UV light. So our last experiment, or our last item that we'll talk about its fluorescence, is actually tonic water. Something that people are pretty familiar with. I don't think it tastes very good, but it is really, really interesting because it glows pretty brightly underneath UV light. That's because of a substance in tonic water that's called quinine. Not all tonic water has quinine, but most of them do. So if we take a look, and we'll turn off our studio lights in just a moment. Go ahead here. We'll turn off our studio lights so you can take a look. Look how brightly this tonic water glows. So it's not just lit up because the light is on, right? It's glowing. It's really, really kind of an interesting green color. You'll see it even better when I go ahead and switch my camera back over. But because of the quinine in tonic water, that's a natural phosphor, a natural item, again, just like our minerals, that is able to have a shift in its electron states when it absorbs UV light. So let's switch our camera back over, and I've poured some of our quinine into just a couple beakers. All right, so I've got 2 beakers here, both full of quinine. We'll turn our UV light down at it, and you can see just how kind of interesting the glow or the color of this quinine is. Shift to make sure we can see everything. All right. So it glows this really, really interesting, bright green, bright blue, but we can actually neutralize this. So we said that this property of fluorescence is a property of the atoms or the molecules inside. If we change this molecule's ability to have a change in its electron state, it will no longer fluoresce. We can do that very, very simply just by adding a little bit of salt to one of our beakers. So to this beaker, we'll add just a little bit of salt. And what's going to happen is instead of those electrons being involved in that process of fluorescence, instead they're going to get tied up in the bonds that it's making with the salt. So we'll pour it in, and it's going to fizz just a little bit. We'll let it fizz, and then we'll let those bubbles settle. And once the bubbles pop from the surface, we notice that that quinine is no longer fluorescing. It is certainly not glowing as brightly or really even at all under the black light as it was before. So our molecules, like we said, our atoms, our electrons are being tied up in this interaction with the salt. So salt is actually grabbing onto those electrons, using them to form bonds, which stops them from being able to change their electron state and being able to emit those frequencies of light afterwards. All right, we've got one last demonstration to show you in our episode for Blacklight Science, but this is a great time for us to pause for any questions you might have from home. If you have questions about any of the UV light experiments we've done so far, go ahead and type them in the chat. I'd love to answer some of those before our last experiment. At this time, as always, we'd like to thank the generous sponsors and the donors to the Michigan Science Center. Our funders like Denso and D2E Energy Foundation are allowing us to bring these programs to you at home for free every weekday at 2:30 p.m. If you are enjoying these programs, we would love if you shared these videos on your Facebook page so that more people could tune in every weekday at 2:30. Thank you to everyone who has been visiting the Michigan Science Center's website for some of our at-home science activities as well. We love seeing those, and we love when you tag us in your results as well. All right, so let's see if we have any questions coming in about our experiments so far. If not, like we said, we do have one last experiment that we'll try. So Becky asked, is tonic water safe to drink? The answer is yes. So tonic water is safe to drink. I don't think it tastes very good, but certainly some people do really like the taste of it. You can get it at the grocery store. Tonic water is safe to drink. If you pour the salt in it, it might not taste, it might taste even worse than I think it did originally. So I might not do that. But you can drink tonic water. Just like we say on Echo Live all the time though, if you use something for science, I'm going to recommend that you don't drink it anymore because now it's been involved in a science experiment, and good lab safety will tell you that you should never eat or drink anything in a chemistry lab. Good question, Becky. So Dana asked, why does it need the black light to glow? And that's because the UV light is what gives those electrons enough energy to first jump up in one of those energy states. So we'll take a look one more time at that diagram that we showed earlier. So this is that diagram about how fluorescence works. So when a photon, like a photon from UV light, when it strikes one of these electrons, it gives it energy. That energy then allows it to jump up in an electron state, which really just means that it has right now temporarily a lot more energy, but it is only temporary. So when that electron falls back down to its original level of energy, there's a bit of energy left over that gets emitted from this atom. And we see that in this red arrow, and that red arrow would represent something like visible light that people are able to see. So the wavelength will change after all this process happens, but it really does require the UV light to be the source of that energy change. Good question. And this is high level material here, but really the important lesson to take away is that what we're seeing out of this lamp here in my studio, the purple color we see is not actually the UV light. That is still just visible light. If we want to be sure that UV light is there, we have to look at the evidence from our experiments, right? So we need to think about the quinine, right? After we saw that in the original experiment with the quinine, or the original beaker full of quinine, that actually fluoresces. It absorbs the UV light and re-emits visible light. But after we added the salt, it does not. So we're only ever observing the evidence of UV light because we can't actually see it with our eyes. So John asked, do all fruits glow or just the banana? Not all fruits glow underneath a black light. If you do end up finding one of these UV flashlights or UV light bulbs at the party store, test out some of your fruit, right? You can still eat it after. Shining a UV light on something doesn't do anything to make it non-edible. Check it out. Different fruits will glow at different parts of their life cycle. So as we said with the banana, it really only glows once it starts to become really ripe, kind of around those brown spots. So not all fruits will glow under a black light, but some of them do. And we said that's normally to, or scientists think it's to attract pollinators. Someone asked, how about the thing beside me? I'm unsure what that means. If you'd like to clarify, I will definitely answer that for you. All right, so keep sending in your questions. I am keeping an eye on those, but we do have one last pretty fun experiment to try here on Echo Live. And because I have this leftover container of tonic water, and as I said, I don't really enjoy drinking tonic water, so I'm not going to do that. Instead, we'll use it for one of our favorite experiments, or one of my favorite experiments we've tried here on Echo Live, which is creating a soda geyser. So kind of a repeat on a favorite, but this time, hopefully, we'll get a UV glowing soda geyser just by dropping some Mentos into the remaining tonic water here inside this bottle. So we'll go ahead and take off the glass, or take off the cap, set a couple of my materials over to the side. Now, if you saw this experiment be done on Echo Live in the past, we've used salt in order to achieve the same results. So if you pour salt into Diet Coke, it releases all of its carbonated bubbles and creates a big foamy mess. But you can do the same thing with Mentos. So this is not a chemical reaction. This shouldn't do anything to stop our tonic water from glowing. All it's doing is allowing those carbon dioxide bubbles inside the tonic water to grab onto the tiny little microscopic pores on all these Mentos, and it releases the gases. So I'll grab just maybe 4 or 5 Mentos here. That way we can try to drop all of them in at once. Go ahead and set my other ones off to the side. We'll hit our studio lights. All right, and here is, we'll take a little bit of a closer zoomed in look. Maybe too far there. There we go. All right, so let's take one more look at our glowing tonic water. We can see that it's really, really fluorescing underneath our black light here. We'll go ahead and drop in our Mentos, starting our nucleation reaction in 3, 2, 1. And there we had it, a fluorescent soda geyser experiment. Ta-da, studio lights pop back on. Let's see if we had any last questions in the comments. Joy asked, aren't bananas radioactive too? There are actually a lot of elements or things here on Earth that are radioactive. The difference between something that's really dangerous and something that's not is all about the level. So while really ripe bananas can be radioactive, it's not enough to cause any harm to humans. But that is true. Some bananas at different stages of ripeness can be radioactive as well. All right. Thank you everyone so much for joining us. We hope we'll see you back here tomorrow at 2:30, either on the Michigan Science Center's Facebook or YouTube. We're also live streaming through Zoom. So we hope to see everyone back here for more science experiments tomorrow. Enjoy the rest of your day. I hope you get outside, get to experience some of that UV light, but as always, make sure you put on your protection, your SPF there. We'll see you later. Have a great rest of your day.